You are welcome once again for this tutorial, of which we are going to talk about Bask generation detection. But before that, I would like you to understand that there are different ways of doing the generation and the detection, right? There are different ways of doing the generation detection in terms of the amplitude shift keying. So based on that, you can do asynchronous ASK detection, and you can also do synchronous ASK detection as well. For the asynchronous ASK detection, it's made up of, let's say, a rectifier, right? That's a half-wave rectifier. If I say rectifier, here the rectifier represents the balance modulator. It serves as a rectifier in such a way that it cuts off all the negative aspects, leaving the positive ones. So in that case, we can say it's a half-wave rectifier. And then after that, we pass it to the low-pass filter. And as I said, in digital modulation, instead of, let's say, the low-pass filter is being represented by the integral from 0 to the bit duration of the signal multiplied by the dt. It's our low-pass filter. Instead of writing there maybe low-pass filter and that's that, we just write there the integral from there, and we are going to do some mathematical analysis on that. And then for the synchronous ASK demodulator, you actually use a square law detector to do that, and after that you pass it through the low-pass filter and then a comparator to compare whatever data is coming out, right? That will determine whether it's a binary 1 or binary 0. This is another form of demodulation. It's another form of demodulation that we are going to do. So basically for this tutorial, we are going to focus on the asynchronous ASK demodulation, right? Or binary ASK demodulation, which consists of the balance modulator, which we can refer to it as a rectifier based on the nature of the outputs of the balance modulator, and then we pass it through the integral, which is our low pass filter in digital modulation and demodulation, and also we pass it to the comparator to check whatever data is being coming out, whether it's binary 0 or binary 1. So that's actually what we are going to talk about in this tutorial. So let's quickly go ahead and start with it. So for the generation, as I said earlier on, you pass the data, the discrete data, through a unipolar non-return to zero, and then from there we pass it through a balance modulator. When we pass it through a balance modulator, the resulting output that we are going to get, remember that here is B of t, is going to give us S of t, and I already did that with you in my previous tutorial, and here is the diagram that we illustrated earlier on. So basically this is it. But remember that it's being done with a carrier signal C of t, and the carrier signal is AC cos omega ct, right? And then after the modulation, we are going to get S of t, and as I said, the S of t is equal to B of t AC cos omega ct. So basically the generation is just two analysis that we are doing here. This is the block diagram, so you understand the block diagram. From there, the balance modulator is just a multiplication, so the B of t multiplied by the C of t, which is equal to AC cos omega ct. So let's quickly look at the demodulation, which is the detection. So for the detection, we know that our S of t, which is the output that we obtained earlier on, is equal to B of t AC cos omega ct, and if we are using, let's say, a carrier to detect it, that means that we are using the same carrier that was used to modulate it to detect it, and in that case we can call it synchronous, right? Synchronous modulation, because it uses the same carrier that was used to modulate it to detect it. So based on that, when we are doing the block diagram, as I said earlier on, you pass it through S of t through the balance modulator, and then here it's our C of t. From there we pass it through our integrator, which is our low pass filter, which from 0 to TB, and from there we pass it through a comparator with a threshold of Vt of h, and this will be the threshold that we are going to put inside, right? And our result is either going to be binary 1 or 0, binary 0. So here it's YTB, and if YTB is greater than the V threshold, that means that it's binary 1, and if it's less than the V threshold, it means that it's binary 0. So let's quickly look at the mathematical analysis behind that. So if S of t, or let's say S of t is equal to B of t AC cos omega ct, and then our C of t is equal to AC cos omega ct, then for the balance modulator, our result that we are going to get here, let's say S of t here, it's going to be given to us as S of t equal to B of t multiplying by A C squared, remember we are multiplying them, cos squared omega ct. So this is the output of the balance modulator. So when we get this output of the balance modulator, we need to pass this output through a low pass filter, which is in this case is our integral. And for that matter, we will need some trigonometric identity to kind of simplify whatever we want to do over here. So let's see how we can simplify it. You remember the identity which state that the cos squared omega ct, or let's say cos squared A is equal to 1 over 2 into bracket 1 plus cos 2a. So in that case, our A is omega ct. So therefore, we are going to get 2 omega ct. So this is what we are going to get for this trig identity that we have to. So most of the time, I advise students that they should make the trig identity be on their fingertips. They should try their best, because most of the courses that you do as an engineering student or even non-engineering students, most of them you have to use this trigonometric identity to simplify questions or problems to make sure that they are in their correct form, or in the easiest form for you to solve, right? So basically, this is what we are going to get here. So when we use this to replace whatever we have gotten here, we can see that our S of t is equal to B of t multiplying by AC squared over 2 multiplied by 1 plus cos 2 omega ct. So but remember that it's an integral of 0 to tb that we are doing here. So if we expand it, we are going to get the integral of 0 tb of B of t AC squared over 2 dt plus integral of 0 to tb B of t AC squared over 2 cos 2 omega ct. So with this, when we integrate this, we are going to get B of t AC squared over 2t, and the limits are 0 to tb, plus for the aspects, when we are doing an analog demodulation, when we pass the results stamped output through a low pass filter, whatever that contains the carrier frequency should go out. So for normal analysis, you can eliminate this without even doing doing the integration, right? But for clarity's sake, in such a way that no one will get confused, I would like to do the integration in such a way that you get to understand it very well. But under normal circumstance, you can see that this contains a higher frequency, which is the omega c, and therefore passing it through the low pass filter will eliminate or attenuate that, and therefore we are not going to get this result inside. But let's quickly run through for the integration. So based on this, we can see that the integral of the cos is going to give us the sine 2 omega ct over, remember that the 2 is already here, right? So let me write it here, B of t AC squared over 2, and then over 2 omega c, right? So when we are multiplying this one, we can do it in such a way that we're going to get B of t AC squared over 2t from 0 to tb plus B of t AC squared over 4 sine 2 omega ct over omega c. And this one too, the limit is from 0 to tb. So based on this, let's do some small analysis over here. So when we do the simplification, obviously the zero part for this aspect is going to be 0, and therefore we are going to get that aspect to be b of t ac squared over 2 and then tb, right? And then plus b of t ac squared over 4 sine 2 omega c tb all over omega c, right? Minus sine 2 omega c multiplied by 0 over omega c, also multiplied by the constant. But sine 0 and cosine are the same, so obviously this one goes to 0. So now we are left with this one, this aspect. So that aspect that we are left with to eliminate, let's see how it's been able to, we are going to be able to eliminate that. Remember that the bit duration is inversely proportional to the carrier frequency, and therefore we introduce a constant n over fc. So in simplification, we can say that our n is equal to tb fc, right? tb, which is our bit duration, the rate at which the signals are being modulated, right? So we are going to get something like this. That's what we are going to get. This is tb equal to n. So if we are doing something like this, then we can say that t equal to what? tb, and because we have replaced the t by tb, and if we have omega c t, we can rewrite it as omega c tb, right? And this omega c tb can also be written as 2 pi fc tb, and it's equivalent to 2 pi n, because here the n is tb fc. So if we have something like this, let's quickly compare this one over here. When we compare this one over here, we can see that this is 2, well, let's say 4 pi fc tb, which is equivalent to what? 2 pi n, right? Let's say 2 pi n, but here, because here is 4, we are going to make here 4. This is 4 pi n, right? That's its equivalent part. So we can finally say that we are going to have something like b of t ac squared over 2 tb plus b of t ac squared over the other one, it's 4 sine 4 pi n over omega c. So one thing that you have to note here is that the integral multiple of these ones over here, when n is equal to 1, we are going to get 4 pi, and a normal circumstance is going to give us 0. When n is equal to let's say 0, obviously here it's also going to give us sine 0, which is equal to cosine, it's going to give us 0. So we can finally say that this part of the expression is going to give us 0. So as I said earlier on, if you want to escape this whole analysis, because you already aware that we are passing it through the low pass filter, which is the integral from 0 to tb, you can directly say that since this is having a carrier frequency, which is a higher frequency, the low pass filter in this digital domain will actually attenuate the carrier frequency, and therefore our resultant expression, it's going to give us b of t ac squared over 2 tb. So this is what we are going to do. So in case the other part for the binary 0 is not giving us 0, we could have done the same thing to it and we end up with a similar expression. So if we want the threshold, right, if we want the v threshold, what we need to do is that you add both expressions for binary 1 and binary 0. So for the binary 1 that we did here, our expression is b of t ac squared over 2 tb. But our expression for binary 0, it's 0, so we didn't do such analysis for it. So when you are done, you find the average divided by 2, and then therefore you are going to get ac squared over 4 tb as your threshold. So when you are supplying this threshold here, that is ac squared over 4 TB, and whatever we got here, after passing it through the low pass filter, which is the integral, is also B of t AC squared over 2 TB. So looking at this and then looking at this threshold, the constant is 1 over 4 for the threshold. The constant is 1 over 2, which is 0.5. And here it's 0.25. And so you can see that obviously the 0.5 is greater than the 0.25. So in that case, we will say that whatever data is coming out from the low pass filter here, which is the integral y of tb is binary 1. But in case it was less than that of V threshold, we will see that our y of tb as the output is binary 0. So this is something that you have to take note of. So you can even analyze it in such a way that if you get the y of tb here, which is b of t AC squared over 2 tb, for binary 1, which is b of t to be equal to 1, we are going to have tb to be equal to AC squared over 2 tb. And then for binary 0, y of tb will give us what? 0. So that is all you have to know about the detection of the binary ASK. So in summary, I would like to say that when the received signal, which is S of t, it's having a binary of 1, its corresponding value that we calculated here, which is y of tb, it's being compared with the threshold frequency, which is the threshold value, which is AC squared over 4 tb, of which I showed you how you can get that threshold value. And if it happens that it's greater than the threshold value, it means that it is binary 1. But whereby the received signal, it's actually less than the threshold value. After comparing it, we can say that the output is low level, and therefore the coded digital value or the information in that particular expression is having a bit of 0. So we will end here for the generation detection, and in my next tutorial we are going to talk about the bandwidth and then the power of binary amplitude shift key modulation. Thank you for watching, and see you in my next video.